This is Brian Putt. Today I'd like to talk to you about the value of information and look at this using a simple evaluation of whether someone has measles or not. And it's probably appropriate because we're sitting here in March of 2020 and in the midst of a COVID-19 pandemic, as they say. Anyway, so what we're going to talk about today is the value of information using a decision tree. And then we're going to look at the sensitivity to probability, see what that looks like in the decision tree. And then we're going to do the same analysis using simulation and see how it compares. And we'll also look at the distribution of the value of information. So let's get started here. So here's the story. We have a sickening story of a doctor. He's sitting in his office, and all of a sudden the patient comes in and he's got spots on his face. And he either has measles or he has acne, okay? Well, the doctor knows that 20% of the time people will have measles in this situation. However, not all measles sufferers have spots, and not all cases of spots indicate measles. In any case, the question is, do I treat for measles or not? The frame of the problem is that the test is 80% accurate in identifying measles. That means there's a 20% chance of false negatives. The test also has a 70% chance of identifying the patients when they do not have measles, so there's a 30% chance of false positives. If we don't treat the patient and he actually has measles, it's going to cost us $300. And if we treat them, it costs $100. And so what we want to do is use the information and incorporate that into a tree using an indicator node and a conditional probability. The value of information can be achieved by bringing the indicator node ahead of the reality node. And this will incorporate the Bayes rule. So down here, we see the conditional probability matrix. Here's the reality. You either have measles or you have spots. And here's the probability of the indicator given the reality. So if they have measles, 20% chance that they have measles, but we interpret it as spots. The test does. And if they have spots, we'll get that right 70% of the time, and 30% of the time we'll think it's measles. So this is what it looks like in Supertree. And Supertree goes way back to the 80s, but still available. It is a really powerful analytical tool. It doesn't have a graphical user interface, but it does allow you to easily portray a tree. And in this particular case, we've indicated a decision whether to get information or not. We have an indicator here that depends upon node 11, which is the reality. We make a decision whether to treat or not, and these are the value measures and the Excel model that it links to. And here are the conditional probabilities we just reviewed. So when you run that tree, this is the results you can get. And so we see that the optimal decision shown in red is to get the information. It has a cost of 52. When we do the Bayes inversion of the conditional probability matrix, we find out that we get measles 40% of the time, indicate measles 40% of the time, and 60% of the time we indicate spots. As you might expect, if it indicates measles, I do treat, and if I indicate spots, I don't treat. On the other hand, if I don't get the information, then the best option is actually to not treat, and I'll take my chances with a minus 60 cost versus always treating where I have a cost of minus 100. So the conclusion is we should test when the probability of measles is 20%. But do I have different decision policies at different probabilities of measles? So what we can do is the sensitivity to probability. So down here is the probability of measles. It goes from 0% to 100%. And here's our 20% number right through here. And this y-axis is the cost. So at our 20%, we have a negative 60 if we don't treat, or if we don't get the information. And we have a 52 if we get the information. And you can see that getting the information is always more attractive. Remember, in this case, we're trying to maximize the value. Typically, in this particular graphic, whenever you see a kink, it means there's a change in decision policy. But as we'll see, this is a little misleading right here because it's not granular enough on the probability. So in this section over here, we never treat. If the probability of measles is 0, why would you ever treat? Because you just let it go because nothing's going to happen to them. At the other extreme, if it's 100% measles, you would always treat them. There's no need to test. And so that's why you see this minus 100 over here. So this is always treating, and this blue line is always treating, and down through here you're never treating. And then in here, on the red line at least, you're following the results of the test. Remember, there is no test here with the blue line. And this is actually, we'll see this is going to be straightened out here when we get to SIPmath. We can also look at the cost distribution, with and without. So now there's really only 3 answers in this particular case. A minus 300 if they get the measles and we didn't treat, a minus 100 if we treat, and 0 if we don't treat and they don't have the measles. So there's only 3 answers. And you can see that distribution. Now the value of information is the difference between these two. Now this was done in SIPmath, and it basically is 60 and 52. The question is, what does this look like as a distribution of the value of information? So here's the value of information with 20% measles. There's about a 24% chance the time we are worse off because the patient didn't have measles. Here's his 24. He didn't have measles, but remember we got the test anyway, so we spent the $100. About 16% of the time, that's this 16 over here, we're better off because we saved $200 because we did the test, we treated them, and they would have had measles. And 60% of the time we make the same decision. Well, here looks like the same decision, but that's the 60%. But if I go back one slide here, this distance over here looks more like, 56. So what's the difference? Well, they're the same here, and they're also the same right down here. And if you add those two probabilities together, you get the 60%. So I think this value of information, this distribution, is really useful in explaining to the decision makers where the value is coming from. So how does that sensitivity or probability look when I do it in SIPmath? So here's that distribution. Remember, this used to be kinked when we did it Supertree, and now it's a straight line. So here on the do not get the information, we take our chances until we get to, what does that look like? Maybe 35, 34%. And then we always treat. And with information, here at, looks like about 18%, something like that, we would never get the information, and then we start to get information at about 18%. We know that we get it at 20%. And then when it gets above, 62%, 63%, then we wouldn't get the information again. We would just always treat. Now, this is a little lumpy. When this was done with 2,000 simulations, trials. If I do it with 10,000 trials, you can see the lines get much straighter. So, depending upon how much accuracy you really need, you can run more trials, and that's easy to change in SIPmath. Put together this graphic, which also shows the value of information as a function of the probability of measles. And what we see is the value of information has no value at low probabilities, has no value at high probabilities, and has the maximum value right here, about 34%. That's where the maximum distance is between these two lines. So what could we do with this model further? I'm not going to do it, but as an extension, we could add uncertainty to the treatment costs and the cost of not treated. We could add cost to for a test. Oftentimes there is a cost for the test, and that needs to be considered. And in some cases, there's actually, if it's a time series model, there could be a delay in the project. You can determine the maximum cost we could afford to test, how high would the cost be if not treated before we would always treat? So the 300, what if that was 500 or 600? And how high could the treatment cost be before we never treat? So the $100, maybe is at $200. I mean, presumably the treatment cost would never be more than the cost if they had measles. So anyway, these are things that can be done. Hope you found this interesting, something to play with. Use your decision tree to work this through, or try using SIPmath. You could try it in Crystal Ball or at risk or whatever you want to do. But I think this is a good exercise in learning about the value of information, whatever decision analysis software you might use. Thank you for watching. If you'd like to get a copy of the model, just send me an email at brian@theputz.com. Be happy to share it with you. Thank you.